Hello everybody of PyData Global 2020. My name is Alexandre Abraham and I'm here to present my work, Cardinal, a metrics-based active learning framework. First, small word about my company. So I'm working at Dataiku, which provides a data science platform to democratize access to data and artificial intelligence. We have more than 400 employees across the globe. We're working with many industries. And as you can see on the left, we like to have chill meetings on the fake grass of our office. But I assure you that if you want to join us, we also have proper chair and tables. Since we are not able to meet, you see here my full picture. I'm working at a team called The Lab inside Dataiku, which aims at working on applied research to contribute to research and try to find applications to be integrated in our tool. So in my case, active learning. So what I'm going to talk about, active learning. First, a small introduction. Then I will tell you why we believe that we need metrics. And then I will introduce you Cardinal, our Python package. Let's go. First, what is active learning and when do we use it? So active learning, it's an experimental framework that allows to speed up labeling and reduce the cost to reach the best accuracy of the model. It's typically used when you have a lot of data that is not labeled and you need to label it to start a task. You cannot label everything, or if you just want to speed up the process. Most typical examples are medical imaging, because hiring a radiologist to label data is very costly. You can have classification for diabetic retinopathy, for example, or detecting malignant cancer cells in histological data. You also have name identity recognition. So here you have Prodigy, an interface over the very famous Spacey model from Facebook. You can see that active learning can help labeling by pre-labeling some samples that are already there. And the best is a model, the less the annotator has to work to do. So that's how active learning works. Let's look at the workflow. First, we gather data. Then we have a step that is proper to active learning, which is query selection. So a query is a sample that we want to send to an annotator to be labeled. Obviously, nowadays, training a model is very costly. So we usually pick a batch of this sample, 100, and send them to several annotators. Once we've done that, we get labeled sample that we use to train our model. Here we take a decision. Either we have no budget left, or the model is good enough, so we ship to production. Or we can label more. In that case, we will examine the samples that are remaining and the model to be able to select a new batch of queries. And we loop again until we have exhausted the budget or reached a given accuracy goal. So for us to be all on the same level about active learning, I will present the basics. First, the intuition. So on the left, you can see the MNIST dataset, which is a very famous one. It's a TSNE representation. Of course, in active learning, we would have no label. So the first things to do is to look at the most representative samples. This will be our first queries. And for that, we can look at density or use a clustering method to find the ones that are the most typical in the space. This is called representativeness. Once we have trained a model, we will look at informativeness. So what are the samples that bring the most information to the model? And for that, we will look at the ones that are along decision boundaries in usual. Here in the MNIST, we can look at 9 that look like 7. It's very typical. But actually, I told you that we select a batch of samples, and we may not want to send only 9 and 7 to our annotators. So sometimes we also want to optimize for diversity, meaning we will try to sample the space and look at samples that are scattered all around. So those are the 3 main criteria that are optimized by all active learning methods, although representativeness and diversity, since they are based on distance between samples, similarity metrics, they are usually optimized together. So let's go back to the paper that put the basics of active learning, written by Settles in 2009. So in that paper, it defines the most basic uncertainty-based method. So the method that are based on the prediction of the model. On the left, you see a table with 4 classes, A, B, C, D. Each row is the probability prediction for a given sample. So we have 3 samples. And what we are looking to see now is which is the sample that is the most informative for the model. So only informativeness. One first method is to look at the one with the higher uncertainty. So the lowest top classification probability. In that case, it will be the first one. It has 0.4, which is the lowest top probability among all samples. We can take the intuition of the 7 and 9 that look like each other and say, okay, that's the difference between the two top classes that is important. In that case, we look at the margin. This is exactly that, the difference between the two top methods. In that case, we would select the second sample. Or we can say all the values are useful. And in that case, we take the very classical entropy measure. And in that case, we would select the third row. So obviously, I've handpicked this value to obtain this result. But what I wanted to show you is that even the most basic method on the very simple cases can disagree with each other. And now we'll take a look at more advanced methods just to, again, build the intuition. So here we have, we start with the setting on the left. We have two labels, so from random points. We build up a decision boundary and we optimize for informativeness. So we will look at the samples that are the closest to this boundary. We end up with the situation on the right. Obviously, what happened there is that we optimize for informativeness uncertainty, and we totally ignore this unlabeled cluster on the top left. So what Lee has proposed is to train another classifier for just for the sake of selecting the queries. And this one is attracted to unlabeled samples. And it is implemented by adding in the training set of the SVM these unlabeled samples with the both labels. Since it's impossible to solve, the decision boundary will obviously be attracted to this set. And by doing that, we obtain a better model in the iteration just after. So that's the interest of mixing them. We can also put all them together in one big minimization problem. That's what is proposed by you in 2015. I will not go through all the equation. What you have to remember is just that in this method, we minimize the similarity between query samples. So we do not want the queries to look like each other. It's diversity. We minimize the similarity between the queries and the label sample. So we want to go far away from what we have already labeled. And we want to maximize the similarity between the queries and the unlabeled. So then we will be attracted to a big cluster of with high density. So, and you put all of that in one minimization problem. And that's one way, again, to mix all of them together. I presented this method because I want to look at the results, actually. Fortunately, both of them have worked on the same dataset, which is called Australian, come from UCI. And we see clearly that 2015 in the top left is clearly the best method by far. What's interesting, actually, it's another method called Quire. In both of these results, we see that Quire is not better than uncertainty, not better than random. Actually, all these methods perform approximately the same. So we can look back at the Quire paper. And what Quire in their paper Huang has proven is that they are better than these methods. Not much better than random, but still a bit. And actually much better than uncertainty, which has a very bad score. And this is not what we find in the other ones. So it's very troubling to see these results, and we wonder how to choose the best method. Actually, in a series of papers, Kottke proved that it can be hard to compare active learning experiments. In particular, in the bottom left, he has reproduced the experimental setting that most people use in this paper, which is 5-fold cross-validation, and he has shown that by changing the seed, we obtain very different results. So it may not be enough. And if you repeat this experiment, you obtain what you see on the right, and you see that a conclusion that a lot of people have reached in other domains: confidence interval matters. So that's one thing we can say. We are also try experiments on this data set, and what we found out is that what we call easy task, meaning task on which the selection of the model doesn't really matter, all of them perform very well with a small number of samples. Well, in that case, it's very hard to get a winner because they all get very good performances very fast. So that's what we show on the right. You can see one example on one data set, and on the left, you see comparison that we have made. So on easy task, we see that random and k-means that I will talk about later are bad, but among the best one is hard to say. Whereas on the hard task, we are able to find a winner. So that was our conclusion. But yet, another researcher said even on harder task, it's not that easy. So on the left, you can see a paper called Corset. In their paper, the researcher showed that they are far better than uncertainty and random. And actually on the right, same data set, different model. we see that the proposed method is better, but they compare to core set, which has exactly the same score as uncertainty. So it's hard to say, okay, it's very hard to see what is happening. And the problem is that when you are an industrial practitioner, you have a data set that nobody has ever worked on. So you can compare it to existing, but it's hard. And plus it's a one-shot experiment. So the thing you cannot allow to happen is to be worse than random. And we've seen actually that some of them are worse than random in some cases. So how do I choose my method? And more importantly, how do I say that I'm not doing worse than random? For that, we introduce some metrics. So here you see that we do not have all the answers, but we're starting to work on that. And we already have some outcomes from our study. So first, before getting to build any metric, we need to know, okay, what are we evaluating? On the right, you see what we usually see in active learning papers, meaning a curve that is increasing with the number of iterations. What most people do is just visual inspection of the paper, trying to find patterns like how do they behave in the end? Is there a way in a moment in the experiment where one is better than the other? And this one can be at the beginning. So they make interpretation like that. Others prefer to set really a fixed point in time where they compare them. Or some of them just look at the area under the accuracy curve. For example, that's what we have decided to do to perform all the tests that I've shown you. The problem we have is how do we measure that in real life? Because obviously it's a research setting. Is there a way to get the same information in a real experiment that we are doing right now? So we have a labeled set. It's small. We have done it manually, but it exists. So we can say, okay, let's run classical cross-validation. The problem is that this set is small. This set will grow with time, making the problem more complex. So the accuracy inside this set may actually decrease over time or increase. It's very hard to say. And the problem is that if we want to use this label set to evaluate the performance of the query strategy, we cannot, because it is biased by the query strategy that has selected the samples we wanted to put into. So one query strategy could really explore a small part of the space, we will never know because we only look at the labeled samples that have been selected by the query strategy. Another method is the one used in research, which is, okay, let's take an independent labeled test set. The problem is that we have a business problem. When you're an industrial practitioner and you say, okay, we are going to label a lot of samples just for the sake of validation. Obviously, it brings you some information, but most people will be doubtful that it's worth the budget spent to label them. So really what we wanted to do is to get insight from an independent unlabeled test set. When I say independent, I mean the query strategy is not able to pick in them. So they stay completely outside of the experiment. The first thing we can compute is maybe the exploration, because I've talked about it several times. And what we can look when we have this independent test set is the distance to the nearest neighbor of each of the sample in the labeled set. The more we explore the space, the more this distance will decrease. And that's what we see here. So we take a look at the difference between each iteration because it's strictly decreasing. What we see is that actually it goes low very fast. And it can give us an intuition about how good we have explored the space. And actually what we see, we had to put a log scale because we see that after 700 samples labeled on LDPA, all the methods kind of go toward the same score. Just a bit of a word. LDPA is a data set with data from accelerometer, from sensors, that is used to determine the position of a human being, the goal being to detect when old people will fall when they are at home. So we have found this data set to be particularly complicated in active learning. This is why we focused on this one in this talk. And if we look at these scores across several data sets, we see that random and k-means are the best ones, obviously because they are unsupervised, they are meant to explore. So k-means is just a k-means run on the data, and we take the samples closest to the centroid. So we expect them to be really scattered across the space. So that's one thing. Maybe we want to wait for it to be low enough. Low enough being, we can, for example, select randomly some samples and compare to random. And when we reach a value similar to random, we can stop. So that's one way. Another big question is when to stop labeling. Because if I save some budget by labeling faster, but I do not train and do not stop at the right moment, then I will just spend the same budget as if I didn't do active learning. So one method proposed by Gayum in 2010 rely on the intuition that at the beginning of the experiment, we have a lot of high uncertainty samples. So the variance is low, but all the values are high. During the training, some value will gain more certainty. So we will have a higher variance in the uncertainty score. And in the end, all the values, all the uncertainty are very low. So again, we reach a low variance state. And in the top part, we see that's actually what happens in their experiment. And we see that actually in the scores, in the end, it's not worth labeling anymore. The only problem in that seems to be in this graph that we may have wanted to stop labeling before, but seems to be efficient. Another approach is proposed by Vlachos, which is looking at the average of the scores. And what they see is that when you reach the accuracy plateau, it seems that the scores start to decrease, actually. That's what you see on the left. And based on that, they created an indicator called contradictory information, which takes the score, the uncertainty score of sample divided by the average on all the data, which gives some indicator that decreases. So again, we have some indicator. It's hard to see how to use it yet, but another metric to test. And finally, we have built also our own. It's called contradiction. And basically, we look at the independent test set, and we look at the ratio of sample for which the prediction has changed, because it's maximum boundary over the accuracy. So we expect it, if it goes near 0, it means, okay, the model is not changing decision, so you can stop labeling. Whether it's good or not, keeping the same setting will not help. Same, if it's flatlining, it may mean that we still have a lot of contradiction ongoing, so the model is uncertain, but keeping the same setting doesn't seem to help. So that gives you a bit of intuition. And we've seen that. So here on the LDPA again, we see that the best methods are the ones that have the lowest contradiction in the end. And on the other hand, the worst methods still have a lot of contradiction at the end of the experiment. When we run that on several data sets, we observe that actually the correlation between the two metrics is high, especially when we have good methods, actually, when methods are performing well. When we have very bad methods, the contradiction is not very informative, because in this ratio of sample that changes, some of them may be good changes, but when you have a bad method, they can change labeling for another wrong label. But that's a way to move on this subject. So what happened is that today we do not have definitive conclusion about metrics, but we have a lot of them. We've seen that they are useful in some experiment, and we want to do that on a larger scale. And to do that, we need proper software. So as I said, the active learning experiments are based on a for loop. They can be very costly, particularly if you're using deep learning. So we want a package that will make them easier to write, and that will offer to us some guarantees, like resume in case of error and being able to replay the experiment to ease reproducibility on one side, and to make it easier to compute metrics. So I will go into the details of that in the last section. First, a bit of landscape of the Python ecosystem around active learning. So we have 3 main packages. All of them provide really great query sampling strategies, and actually you can use them together with Cardinal. I will focus on the specificities of each one quickly. So first, Modal has a minimalistic design. It focuses on ensemble approaches where you use several classifiers and a voting system to select the queries. And it provides, that's what's interesting for us, an active learning object that allows you to run experiment with in-memory caching. So you have easy access to previous values. Doesn't bring you resuming or any fancy feature. We have AliPy that has been created in Nanjing University. It provides exclusive method along with really a wide range of query samplers. So a lot of them are from this lab, but you also have different ones from the literature. So it's really a good one if you want to experiment. And they provide an idle experiment object that is the experiment with this caching. So you can resume an experiment that has failed, but you cannot replay. And finally, we have illibact, which is more oriented for performance. So I would say the one you would use if you are doing active learning at scale, so a lot of data. It has compiled C code, so it can be a bit difficult to install. It features some exclusive query sampling tool, like meta-active learning. Not go into the detail. Doesn't provide a lot of utilities, noisy labeler for some experiment, but otherwise it's up to the user to do most of it. So the philosophy of Cardinal is close to what you can find with scikit-learn. We do not want to integrate all the research method of the literature. So we only want to have tried and tested query strategies and metrics. For that, for all the method we integrate, we provide detailed examples and experiments. And obviously, we want to ease the reproducibility and metric research by providing a replay of experiment. We also have a human readable cache for easier research. And so far, we have classical query strategies, some strategies that come from a paper that I will describe just later, and a lot of examples to introduce the active learning if you do not know the domain and want to know more. So let's go a bit about the interface. It's very close to the scikit-learn one because actually we discussed with people from scikit-learn which are specialists in terms of Python architecture. So you have a base query sampler that has a method fit and select sample. And from that, we derive two use cases. If you're using a score that is for all the samples, you can use a scored query sampler, and that's how we code uncertainty methods. If you want a clustering-based approach, like the one I described, that runs a k-means and find the sample closest to the centroid, you can use a k-centroid sampler interface. And at the top right, you see the kind of example we provide that is comparing all samples on a toy dataset, but you can do that on one of your experiments if you want. Now a bit of code. Small warning, it's not final until the end, until version 1.0. So if you want to contribute, if you think that we are doing things good or bad, please tell us. It starts like a classical experiment. So we have the train, a small configure dictionary, we'll come to it afterward. We have a classifier, we have a query sampler, in that case the margin, and we have some batch size we want to explore. The first thing to do is to instantiate a replay cache. So we have the resume cache that allows you to run an experiment once and cache the data accordingly. But it clears them afterwards so that it doesn't take too much disk space. Or you have the replay that stores everything and allows you to rerun an experiment. First thing to do is to declare a variable. That's the values that will be cached after each loop of active learning. Here we take selected, which are the indices of the selected samples. We declare our main loop. Here we have a cache iter util that will go through the batch sizes and that will provide automatically the method, the value of the previous loop that we have put here for the selected variable. So the advantage of this is that if you ask for a value that was 3 iterations before, this will be kept in memory to avoid the reading and writing to disk too often. Classic active learning stuff, we feed the classifier. We want to store the accuracy. Again, we provide a util for that. It will be stored in a SQLite database. Then we feed the sampler and we update the value in selected by using the previously selected indices with the new ones. And what happens is that all of that will be cached and we will be able to use it to compute metrics afterward. So if you have forgotten to put a metric in your loop, here we didn't put any, you can still compute it afterward. It will be done thanks to the data that has been cached during the experiment. Obviously, there it will be read completely from disk. So now let's see what has been saved by Cardinal. So on the left, you see what is on the disk. We have a nice tree. So with the cache, the method, which is margin. And for each iteration, we have the selected values that are stored on disk. And on the right, you see the database that we explore using the very good Python package dataset that allows you to explore SQLite database easily. And you can see if we take the table accuracy that we have saved all the accuracy along the experiment. And that allows you to actually perform several experiments in parallel because the database will handle the concurrent access. So let's talk a bit about reproducibility. Like I told you, we provide a method that has been presented by Zdanov. This query strategy uses uncertainty to pre-select, for example, 10 times the batch size that we want to select. So we first use uncertainty, which is not costly. And then on 10 times this batch size, we run k-means. And as usual, we take the sample closest to the centroid. So this is a method that scales well and that has good performances. Actually, what we've done is that we've reproduced the results and provide them in Cardinal. So you can see on the MNIST dataset that we managed to reproduce the results. Even though the confidence intervals are bigger than in the original paper, we reached the same conclusion, which is that the proposed method is better than uncertainty or random. On CIFAR 10, they do not reach a clear conclusion. We did not reach it yet. We see that uncertainty is better than random. Actually, the other methods are competing. They have similar results. One thing that we note is that we have an accuracy that is much better than the one in the paper. And that may be due to the number of epochs or parameters that are not specified in the paper. So we do not have an answer yet from Zdanov because we are in the process of releasing it into Cardinal, but we expect to have an answer as soon as possible. That brings me to my conclusion. So active learning is still an active field of research because we are still acquiring a lot of data in a lot of different use cases. And the experiments that are provided are often hard to interpret and to reproduce. That's why we propose some metrics. We still have no hard conclusion because we need to test them on a wider range of use cases. So we have preliminary results, but we are still working on it. And we are doing that using Cardinal that we have made available to the whole community. We have big ambition. We want to revolutionize active learning, of course, like everybody. But for now, we convey only minimum functionality. So if you want to contribute, please reach out. And obviously, if you want to contribute to that from the inside of Dataiku, do not hesitate. We are hiring. Thank you for your attention. I will now answer your question.